You can see that I have better quality this time. I'm not doing this at 3 a.m. in the morning. I actually have time, cause you know why? You know why? Scheiße. So I have time to actually make something. I don't have to do all this bullcrap schoolwork, right? I can use my ADHD to my full potential. I already created this video, but it was so bad quality. I used my webcam actually to use the video, right? There we go. I used the webcam, right? Ooh, I see that. I think you see that too. The whiteboard is shining bright like a diamond, right? This is disgusting. I have no idea why it's so. We left off part 1, right? So we discussed what a derivative of a function is, right? What is it? It's a slope of a line, change in the f of x value over the change in t value as the change in the t value approaches 0. We discussed various limit properties. And I can't read this. We discussed what E is. We discussed E. I'm pretty sure that's what I wrote, but whatever. Right, so let's do a little review, right? I don't know where to follow, right? E, right? We discussed that E is equal, ooh, wait, no. That would have been brutal. E is equal to the limit as n approaches infinity of 1 over n plus 1 to the power of n. I am pretty sure there's a better proof than just intuition. But yeah, Euler-Friend's constant, and that's why it's called Euler's constant. It's called Euler constant, and he found a lot of things. He loved to experiment with it. He was like, "This is my boy right here, E. Let's do more with that, right?" And I want to also verify. So, what's e to the x? E to the x is the limit, and well, it has two definitions. As n approaches infinity, of x, right? What is e to the x, right? Black pen. Blue pen. Yay. E to the x, right? It's glare. It's disgusting. I hate how this shines on it. Yeah, I can actually do this. It looks better. Limit e to the x. Limit as n approaches infinity of x over m plus 1 to the power of m, right? That's another limit property that Euler found. And then of E constant, not a limit property, but it's just this is also equal to the limit as n approaches infinity of 1 over n plus 1 to the power of n times x, right? So these two intermingle, right? Finally, a better way to say this is e to the ab is equal to the limit as n approaches infinity of a over n plus 1 to the power of b times n, right? So he found that, right? Just a little info. I'm not sure that pertains to that does pertain to another proof for e to the pi I, but not that proof, right? This constant is beautiful, right? It helped him discover, I don't need a paper anymore, limit properties, right? Many different limit properties, like log a to the b, right? Or derivative properties, log a to the b, right? And he also found, right, ln x, right? What is ln x, right? What is a logarithm anyways? A logarithm, so if f of x is equal to a to the x, right? Then the inverse of f of x would be equal to log a to the x is equal to b, right? Wait, hold up, a to the x, wait. Log a to the, log from ab is equal to x, right? That's what it is. It's finding what power of a is equal to b, right? This is a logarithm, right? And many people had trouble with finding the derivative of log a. So what they did was they used Euler's constant. They found the derivative of ln x, and they found that was 1 over x, right? And they can use this definition to help with logarithms, right? And you may be saying, oh, well, can't you just use that with other constants? Well, 2 to the x, the derivative of 2 to the x is not equal to 2 to the x, right? It's not like e, right? Because 2 to the x is equal to 2 to the x times the limit as delta x approaches 0 of 2 to the delta x minus 1 over delta x, right? And this portion here is not equal to the limit as delta x approaches 0 of e to the delta x minus 1 over delta x, right? They're not the same. No, they're not nowhere near close, but they're just not the same, right? They're, well, if you're thinking about decimal places, they're nowhere near close. This is the only exponent where that is equal to 1. If you actually plug that into a graph right now, put x to the power of 0 minus 1 over, okay, well, I know there's a way to look at this, but, you know, if you plug this type of function on a graph, you're only going to get e to the x where that is equal to 1, right? And it helps with many other things, ln x, right? So the same thing applies with logs. You can't find it. Usually it wouldn't be conventional to find the derivative. There would be no derivative, right? And e helps with a lot of things. It helps with many things. Compound interest, money, physics, different physics problems, differentiating, like we already said, exponential functions, which I meant to say, exponential functions, and many other different properties. So that was very important. And Euler began to research more, and that's how he came up with, let me erase this. That's where he came up with the fact that that's where he came up with the fact that, right, e to the pi I is equal to -1. This is a lot of frames per second. I thought this was going really fast, but this is really good. iPhone 8 cameras are really good. E to the pi I is equal to -1, right? That's how we found out. So how do we get to this point, right? Well, like we discussed last video, it involves Taylor series, right? And Taylor, the bright boy, he was a big boy. He helps find many different things, right? So I'm gonna list out the many different types of functions, right? Trig, we have trig functions. We have logarithmic functions. We have exponential functions. We have linear functions. We have constant functions. We have a floor function, floor/ceiling. They're really similar. Trig, log, exponential, linear, constant, and polynomial functions, right? Right? And he wanted to find how to convert all these into a polynomial function with infinite series, right? He wanted to find that, or maybe he just found that because he's IQ. Well, we can cross out one thing. This is polynomial function. A linear function is just a polynomial function raised to the power of 1, right? Maybe plus or minus a constant, right? And a constant function is equal to a constant times x to the power of 0. That also goes out. And a ceiling function, well, you can't find a polynomial of that. That is impossible because it really has a lot of undefined values and it has a lot of limit breaking barriers. It's horrible. It's really good with it's with algorithms and computer science, but like it's just bad with graphing. If you want to analyze that function, go fucking do it, because that's really annoying. It lacks a lot of continuity, right? These aren't all the functions. There's more. There's error. Error. No, there's actually an error function, I'm pretty sure, and a sine. There's a lot, hyperbolic trig functions. Just a lot of stuff, but we're only going to be dealing with the trig functions and the exponential ones, right? With infinite series. What is a series? Before I actually get into it, a series is, right, so what is this? You gotta know this notation, right? It's just the notation, don't be scared because, I've seen that in Big Boy Maths. I've seen that in Big Boy Maths because a lot of movie producers don't know how to actually use math. Series from n equals 0 to 5, right? Let's do something simple. n, right? What is this equal to? Right, well, this is stating we're summing the function of x from n to 5, right? So this is also equal to summation of f of n from n is equal to 0, 5, right? Or you could also say this is f of 0 plus f of 1 plus f plus f of 5, and that's what it's doing. It doesn't always have to equal a constant like this, but yeah. So let's actually solve this, right? So we start from 0 to 5. You plug in 0, that's 0, plus 1, which is 1, and then you plug in 2 and you get 2, so you add 2. You plug in 3, then you get 3, you add 3. You plug in 4, you add 4, and then you plug in 5 and you add 5, right? So you add all this together, and what do you get? 9 plus 11, 12, 15. You get 15, right? Cancel the 0 because fucking who cares about it. So that's 15, right? So that's what a series is. It doesn't always have to be constant. It doesn't always have to equal something. It could just be like, say, sum from n is equal to 0, 3, x, n, right? This is x, and this is n. They're two different things. It's asking for the sum from n, not x. So this would just be 0 times x plus 1 times x plus 3 times, plus 2 times x, and plus 3 times x, right? So this is just equal to 6x, right? 6x, right? 6x. And you notice how it's not evaluated because we're only evaluating at n. these are the parameters. There can only be one parameter for summation of stuff. If you want to have multiple parameters for summation, then just do a double, whatever. But yeah, that's what it is. It's just a sum of x from x is equal to 0 to n is equal to f of 0 plus f of 1 plus da 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 plus f of n. Continue doing this until you get to n, right? You finish at n and you're done. You got the sum because you're cool and you're epic. I'm game. So yeah, that's sum, right? I'm gonna keep this in. So one of the rules, right? Because we're gonna need that for Taylor series or helping. There's just a notation for that. You can write this, fine by me, but this is much easier to write down if you just want to quickly put in a finite thing. Because if you keep on writing that on a test, or if you're trying to do this complex problem, whatever. Taylor series, right? What is Taylor series, right? So, I already told you what Taylor series is. No need to reiterate myself. So let's say we want to find e to the x, right? What is that equal to? Well, e to the x would equal to black pen, red pen, yay. C, some constant, right? Some first constant, or I'll call it the zeroth constant, time, zeroth constant, right? Zeroth constant, right? This is a polynomial. This is plus, right? Some second constant times x, right? X squared, my bad, plus some final constant of x to the power 3. No, not final constant, plus the third constant. You continue doing this infinitely until you get to the constant of n times x to the n, right? This is essentially what e to the x is, right? Because if you notice, right, if we add one constant, right, to e to the x, this is the graph of e to the x. This is 1, right? This isn't the graph, but, you know, this is a rough little sketch. 1, right? If we have constant of x, right, then this is what the constant looks like. If we have x, this is what x looks like. If we have x squared, this is what x squared looks like. If we have x to the cube power, this is what x to the cube power looks like. And if we have x to the fourth, this is kind of what like x to the fourth looks like. And as you see, more and more, as you increase and dilate, right, the function, right, it kind of goes and spoons it, right? Here, let me use this marker to check it out. Kind of spoons the function. The new polynomial function eventually spoons it. And it looks really, really accurate. So what's the most accurate we can get? Infinity. Infinity. And my mom. Don't get any ideas. My mom is not my dad, but she's my mom. So yeah, right? So yeah, that's what Taylor series is. And as you notice, you may be thinking, well, does that work for all functions? Are you sure? Because does it spoon every single function? Say my function looks like it's really sharp, right? Say it's like really wonky, right? Say it's like that shit. There is probably a function for this. There's always a function of something. You can label it, even if it's. I'm not gonna say piecewise. I said it. No. You can't find this because at a certain point, at a certain point in some functions, like, I'm pretty sure it's logarithms, right? Logarithms, since it's infinite, right? This is the function of a logarithm, right? This is a rough estimate. I'm always gonna say rough estimate. When I say this is a function of it and I draw a graph, pretend like I'm saying rough estimate, because that's what I'm really meaning. the rough estimate of the logarithm, right? If we find a polynomial, this is infinite, right? So what are we supposed to go? Same horizontal line. It's not continuous at every point, so there's no Taylor series. It's not continuous, you know. Pretty sure continuity has to do with Taylor series. You know, if a function approaches this, it has a vertical line, like say it's like this, then you don't have a Taylor series function. If it does this, then you don't have a Taylor series function. Discontinuous functions, you can't have Taylor series, right? Some functions are discontinuous, you know, and some functions just can't do it because they're pieces of crap. So yeah, how do you find the first constant? How do you find the first constant? No. How do you find the first constant? How do you find the second constant, third constant, fourth constant? All the constants, right? How do we do this? This looks impossible. Well, maybe not. Maybe not. Right? If this is one constant, right? How do we get this constant? E to the x is equal to a constant of 0. How do we get to that constant? If this is a function of x, and each x relies on what we put there. You thought of it, hopefully. This is nothing but a y-intercept, right? If you plug in a graph, right? This is the y-intercept, right? This is the y-intercept of that graph, right? As everything approaches 0. So we remove all these constants, right? We remove all these constants, and we get e to the x is equal to c to the 0. So we plug in x, we get e to the 0 is equal to c. Sorry for the interruption. I had to do something. I'm a teenager. What is any constant to the power of 0? What is anything to the power of 0? Really, what is your mom to the power of 0? What is 0 to the power of 0? No, just kidding. We don't want to get into that. What is anything to the power of 0? Except 0 to the 0, infinity to 0, and all this weird crap. That's 1. 1 is equal to c to the 0, right? So now we have one thing. Congratulations! Out of every single infinite constant, we have one. Round of applause. So now we can rewrite this as e to the x is equal to 1 plus something times c to the 1, right? Plus something times x squared, plus times x squared, and plus something times x to the cube, right? And so on. Well, let's actually just isolate this real quick, and so on. I don't want you to get confused, right? That, right? That's what it is. This is e to x to the n. Don't be weird. Just how about if you want me to this is plus plus x to the n, x to the n, right? Right. So now, how do we find the first constant? You may say this is impossible. How? Well, I want you to know something that I didn't tell you. There's a quick secret. The derivative of a x to the n, a polynomial, right? Derivative of a polynomial to the power of n, right? Well, this is actually equal to n times n minus 1 times x to the power of n minus 1, right? Right? A constant is equal to constant times x to 0. Right? So what's the derivative of a constant? That is equal to c times 0 times x to the negative 1. And we notice that this is multiplying it by 0, right? So none of this matters, and the derivative of any constant is equal to 0. So we need these two properties to understand what's going on next, right? So how do we get rid of any of these x values, right? You may be asking. That's cool, okay? Jacob, but I don't know why you told me that. Well, if you notice that, we want to get rid of the next constant, right? So if we find the derivative of this, right, this would be e to the x is equal to c to the 1 times the derivative of x. Oh wait, my bad. No, not my bad. This can off. That can go screw itself. E to the x times c1 x, right? The derivative, no, equals to the derivative of a constant of 1 times x plus the derivative of a constant of 2x squared plus a derivative right, constant of 3 x to the cube